Hey guys, today we'll be solving LeetCode number 162, find peak element, medium question on LeetCode. Now first, before I get into anything, what is a peak element? A peak element is essentially if we're given, let's say 3 over here and we're considering 3, if we're given 2 and 1, that means 3 is a peak element. What do I mean by this? Is essentially that if we consider the index I, so let's consider an array and an index I, well, the index over here, the value at that index is greater than the one that we can find at I minus 1, and it is also greater than the one that we can find next to it. So essentially the left and right neighbors are less than the value given at this I. Alright, so that's what they mean by peak element. Now there is an O of n approach. You can check your leftmost, then you can check your rightmost, and then you can run a loop from your second element to your second last, checking for a peak element. And how? Well, just code this up. Now the main thing that I want to get at is the O log n approach that they've said we should aim for. If you guys have studied your time complexities, then O log n generally means, well, binary search. Alright, and if you know anything about binary search, then the thing with binary search is we decide on which way to cut the array based on the fact that the given array itself is sorted. But in this question, there are no promises that the array itself will be sorted, and as given in the examples, the arrays are not sorted at all actually. So how do we actually figure out which part to cut and which part to not go for? And the answer for this question is actually pretty simple once you understand the logic behind it. So 1 2 3 1, let's consider this example, okay, taken straight from LeetCode's example 1. Let's run a regular binary search on it. So let's keep our L 0 1 2 3, and remember they want us to output the index of the element, not the element itself. So in this case our peak element would be 3, but I'll get to how we got there in the first place. So let's run a regular binary search. We have 0 and 3, so 0 plus 3 divided by 2, floor it, we get 1. We are considering 2 to be our mid right now. Let's see. So now that we've ended up at 2, let's consider it with the adjacent neighbors. Okay, so when you want to find a peak, in essence it's essentially like finding the maximum, right? The maximum being in the sense that, well, since it is greater than its neighbor, you could consider it to be a local maximum at that point. Yes, you could. So when we're given this choice of sitting at 2, and we're given this choice of moving to 1 or moving to 3, and we want to try to find a local maximum, which one do you think makes more sense? Obviously going to the 3, right? So could we say that, well, if we are interested in going to the 3, then we can cut our array in half by, well, cutting our binary search like we normally do. So it's exactly that. We will cut our array in half now. We'll consider L to be that and R to be 3. Now we will do 3 plus 1 divided by 2, that's 4, right? Divided by 2, that's 2. So now we are at 3. Now that we are at our peak, how do we well, first of all, determine that it's a peak? Now the thing with this is, the reason why this question is so tricky is because even I was tempted to just do a mid minus 1 and do a mid plus 1 and just check it, and then if it is true, just return mid and we're done, right? But it's not so simple, first of all, because you would end up running into edge cases where your length has to be greater than or equal to 3, and you will run into a lot more other problems. So, well, if you can't return mid, how do we keep a track of what the peak element will be? So, well, the first thing that we can do is apply the same check that we did with 1. We check the one that's ahead of us, let's say 1 in this case. If we wanted to find a maximum, would we really go to 1? It wouldn't make sense to, right? So let's do the same exact operation. Let's cut it down. Let's make it 3, 2 to 3 now. And let's do 1, 2 as our L, as our R. 1 plus 2, divide that by 2, we will get 1. Now we're sitting at 1, so we're back to 2. We're back to 2. But, like I said, we will compare to the one that's ahead of us. Well, 3 is actually greater than us. So are we the maximum? Absolutely not, right? Because well, we are one index ahead of us is already greater than us. So there's no point. We will shrink our array to 3. And we will run binary search in this scenario for only L is less than or less than R. Not equal to, just less than R. Specifically as shown in this example over here, because we will never be returning mid. So now we have our L stuck at 2, R stuck at 2, and well, this loop will terminate, right? So our answer though, if you saw, well, still somehow ends up at the peak element. So all we have to do at the end is just return your L. That's pretty much it. So how do we get here? Well, simple, just check the neighbor ahead of you and just see, hey, if you're ahead of me, am I interested in the ones that might be below me? No. So I'll just shrink my array towards you. And that's literally it for this question. You don't get tempted to check your neighbors and then immediately return mid based on that. Think about what your approach should be to finding that peak. So while L is less than R, mid right now, like I said, literally just do the same exact check that I'm doing. If we are less than the one that's ahead of us, then well, shrink the array. So left now just becomes mid plus 1. However, if the one that we're standing at, right, is greater than or equal to the mid plus 1, right, and they've said that they don't give us every single element as distinct, so we have to assume that it might be flat in the sense that 3 3, right? So greater than or equal to mid plus 1, so that would be our else, right? Well, if we are greater than or equal to mid plus 1, there's a good chance we might find our peak on the other side, right? And even if we don't, that's completely fine, but we might find our peak on the other side because the right side is now essentially useless, as you could say. So well, we will consider the midpoint. However, we won't do mid minus 1. Okay, this is another part of the trick in this question. We don't consider our mid minus 1 because we want to include the mid as a possible answer in this scenario, right? Because we haven't checked whether it is equal to mid minus 1, we just assume that it's greater than or equal to mid plus 1. So we will keep it as an R. We'll keep it in the array that we want to check at, and at the end just return L. So the first key idea is don't do a minus 1 over here, because we will consider it in the grand scheme of things. We will consider our mid within that array. And how do we determine which way to go? Well, just check your neighbor. If you are less than him, then you would want to squeeze towards him.